Today we're going to be talking about intermolecular forces and figuring out which molecules have which intermolecular forces. So there's a couple things that we need to talk about. First, bond polarity. Bond polarity should be pretty easy. It's based off END. So if the bonds in the molecule have an END that are 0 because they're the same element, then they're nonpolar. If the bonds are different elements, their END is something other than 0, and we're going to call them polar. Now, obviously, that is a oversimplification, but for what we need to do, that works. Now, molecule polarity. Molecule polarity is based off symmetry, which is the snap rule. So if the molecule is symmetrical, you draw your two lines of symmetry, and therefore it's nonpolar. If the molecule is nonpolar, it has London dispersion forces, no exceptions. Now, if the molecule is asymmetrical, then it's polar. So here's what's going to happen. 99% of the time, it's going to have dipole forces because they are the go-to for polar molecules. If it is F, O, and N bonded to H, like HF, H2O, or NH3, there are others, but these are the big three. If it has this scenario, F, O, or N bonded to H, and it has to be directly bonded to H. You can't just have F and or O and H in a compound. They have to be directly bonded to each other, the same for all of them. Then you have hydrogen bonds. So it's really only these three examples that we have to worry about. Now, what happens with intermolecular forces? Well, as the intermolecular forces increase or get stronger, the boiling points get higher, the molecules move closer together, and you can ultimately cause phase change. So London are the weakest, then dipole, then hydrogen are way, way, way stronger. So I'm going to do a couple practice problems with you, and then you're going to do the rest. So let's do, I guess, the first two, actually. So for the first two, I'm going to let you skip drawing out the bonding. So for this one, we have an END that equals 0 because it's two H's and they're the same element. So therefore, nonpolar covalent. And for the second one, we have an END, which doesn't equal 0. And therefore, we have polar covalent. For our Lewis dot diagrams, H2 just looks like that. HCl looks like this. And let's do the next one. END also doesn't equal 0. And this is HF. Don't forget about the lone pairs. The bottom two are polar, so they need a polarity arrow. And now let's talk about molecule polarity. For molecule polarity, you have to draw two lines of symmetry. So for the first one, it is symmetrical, nonpolar. Therefore, based off this answer, it has London dispersion forces. For the next one, HCl, it is asymmetrical and polar. So we're here. It does not have F, O, or N in it at all, so therefore So yeah, the easiest way to figure out if you're dipole, it's very simple. If F, O, or N are not in the picture, then it's automatically, if it's polar and it doesn't have F, O, or N, it's dipole. The only time you even have to question it is if it's polar and F, O, or N are present in the molecule, then you have to think, well, is the H directly bonded to them? If it is, it's got hydrogen bonds, like in this next one. It is asymmetrical and therefore polar, but it happens to have hydrogen bonds because it has F, O, or N bonded to H, or you could say because it's one of those three. Now, obviously, don't be confused. Hydrogen bonds is not a form of a bond. Like, that's not a hydrogen bond. A hydrogen bond is when two HF molecules attract to each other. So like if I had, one HF here, I'm just gonna draw this minimum amount possible. And here's the other HF. And then we know that there's an attraction between them, right? That attraction is the hydrogen bond. Okay, it's called a bond. It's not really a bond, it's an attraction. A better word for it would be hydrogen attractions or something like that. but they never did. They didn't think that far ahead, and so we've got to deal with it. I do want to go over one on the back, or maybe two. So when you get to the back, the ones that throw students off the most are going to be these guys, because I'm not going to do the END, but a lot of people will look at this and say, well, there's hydrogen bonds here, because look, there's H and F make hydrogen bonds. It's not always the case. So let's draw this part out. So if I draw this one out, I'm not even going to include the polarities or any of that. First thing is, if you do the symmetry for this molecule, it's actually symmetrical, and therefore it's symmetrical and therefore nonpolar and has London dispersion forces. The reason it doesn't have hydrogen bonds is because the F is bonded to the C, and then the C is bonded to the H. In order to be a true hydrogen bond, or to be real hydrogen bonds, the F has to be directly bonded to the H, and it's not in this case. So be aware of that. And also, the reason I picked this one is students tend to draw this one asymmetrically and then think that it's got dipole forces, or sometimes hydrogen bonds, depending. So this one gets messed up a lot. In 3 dimensions, this is a symmetrical molecule, so I would always recommend drawing it symmetrically if possible, or always, not even if possible. Draw it with symmetry no matter what, because if you were to use the 3D modeling of this, you would see that it is fully symmetrical in 3D. So drawing it asymmetrically in 2, it is really kind of doing yourself a disservice, because that's not the way it really looks.